Yep, we're good to go. All right, so circular motion, quite literally an object going around in a circle. So if you have an object that's going around in a circle with a constant velocity, a constant speed, then the velocity of that object in circular motion can be given by this equation over here. Or let me write it out on the board. So we have velocity equals to 2 pi r over t, where v is the velocity of the object that's going through circular motion. R is the radius of the circle that it's going around in. So if we have an object over here that's going around in a circle, let me try get it as circular as I possibly can. Just assume this is a circle. That would be R, to the center around which it moves around in a circle. Then t is the time period, or the time it takes to go around one full circle. Well, this works because if you remember, 2 pi r is simply the circumference of the circle, and since t, or the time period, is how long it takes for it to go around in a circle, this gives the velocity by distance over time. Now let's continue. Then we have the concept of angular velocity. So angular velocity is the rate of change of the angle of an object from the center. So let's say over here, the object is over here now. A few seconds later, it will be over here. And there is an angle now over here. The rate of change of this angle, how this angle keeps increasing while going around in the circle, is known as the angular velocity, and it's given by omega. So omega equals to change in angle over change in time. And this can also be given by 2 pi over time period, because if you remember in radians, the total angle, or 360 degrees in radians, is the same as 2 pi, and that is a full circle. That is how much the angle changes by in one whole period. So 2 pi over the time period. And from waves, if you remember, we had time period equals to 1 over frequency. This applies over here because this is also a simple harmonic motion in a way. It's going around with a constant period. So the frequency is just going to be 1 over time, or the other way around, as I said over here, time equals 1 over frequency. So you can equal this to 2 pi f, where f is the number of complete oscillations, or number of complete circles this object goes through in a second. And note, the unit for angular velocity is always in radians per second. You should always use radians while doing circular motion, unless the question asks you to do otherwise. Now, moving on to the next part, that is centripetal acceleration. So centripetal acceleration is the acceleration towards the center of the circle that's allowing for circular motion to take place. So when an object is going through circular motion, let me just clear things out. So let's say that's the center. And here we have an object that is constantly moving and has a velocity in that direction, a velocity of v. Now you have a force that's acting towards the center, which is known as the centripetal force, the force that acts towards the center. resulting in the ball to go in a circular motion. While this tangential velocity of the ball never really changes, but the direction in which it's going is constantly changing because of the centripetal force, and as a result of that, it goes around. Now, the centripetal acceleration. So we know that acceleration equals to the change in velocity over the change in time. In this case, we have a constant velocity. I mean, the magnitude of velocity is the same throughout. However, what changes over here is the direction in which it changes. So now, let me equate this to something else. So if you remember, we earlier had the angular velocity equals to 2 pi over time period. Sorry, nope, I don't need that over here. Just give me a second. Right, so at any given moment, the ball, or let's say this object over here, will travel a distance. Let's just label it as distance actually. I'll just call it x. Will travel a distance of velocity, because velocity is constant, times the change in time. And the angle that will be swept around when we cover this distance, so let's say the distance is from here to here, and we call that to be x. X is this arc length over here. So we have a change in angle also as it moves from here to here of, I'll just say it's delta theta, the change in angle. And this length, because we're giving it in radians, the arc length can also be written as the radius times the change in angle. This is just using our knowledge of circles. So now we can equate these two to each other, giving us velocity times change in time equals to the radius times the change in the angle theta. And we can get velocity equals to the change in angle over the change in time times our radius. This gives us one more equation that can help us figure out velocity in terms of angular velocity and the radius. Here we have another equation that can prove to be useful. Sorry, I stepped back a bit. I just realized that I forgot to define this. Now let's move along. So now moving back to acceleration. Let me get rid of this. Now I also showed you that our velocity equals to the change in angle times the change in time over the change in time times the radius. So which means our change in velocity is actually equal to the velocity times the change in angle. That is what our change in velocity is, because the magnitude of velocity remains the same. It's just the direction that's constantly changing. So I can bring that in over here. Change in angle over change in time, giving us velocity times our angular velocity. Now we also know that from earlier, as I found out, that our velocity equals to angular velocity times the radius, which means angular velocity equals to the velocity over radius. Now I can substitute this in over here, giving us v squared over r, which I believe is given in your data booklet. So centripetal acceleration can be given by the velocity squared over the radius. Now using this, I can also derive the other equation for centripetal acceleration given to us in the data booklet, which is 4 pi squared times r over period squared. Note over here I've also used angular velocity squared times radius. I can use the same thing over here to find that out, because like I said, velocity equals to angular velocity times the radius. We get angular velocity squared times radius. Now let's try to show how acceleration equals to 4 pi squared r over time period squared. So using this equation, we already know that acceleration equals to velocity squared over radius. Now we also know that velocity equals to 2 pi r over t from earlier. Now let's substitute this in. So we've got 2 pi r over t squared divided by r, and this equals to 4 pi r pi squared r squared over, I just realized I didn't really write r over here, r times over r times time period. I can get rid of that, giving us the equation we were targeting for earlier, 4 pi squared r over time period squared. Sorry, I forgot to write that down. This also gets squared, and that's how you get centripetal acceleration. Now centripetal force is the force towards the center of the circle, and using force equals mass times acceleration, we can tell that the centripetal force in this case is going to be equal to the mass of the object that's traveling in the circle times centripetal acceleration. We can take it to be either v squared over r, giving us m v squared over r as shown in the data booklet, or we can use angular velocity squared times r, or omega squared r, giving us m omega squared r times radius, and that is centripetal force. With that, that brings an end to the first part, that is just circular motion. Before I move on to gravitation, are there any questions? Anyone have any questions? Just feel free to ask before I continue on to gravitation. And if you're clear, just maybe say a yes in the chat so I know I can move on. Alright, cool. I'll move ahead now then to 6.2, laws of gravitation. Well, the SL part doesn't really cover much of laws of gravitation. Most of it falls under chapter 10 fields. Over here it's just superficial. All the main stuff you learn is in chapter 10 fields if you're doing HL. If you're in SL, there's not much you need to know, just what I tell you. So Newton's law of gravitation. Newton's law of gravitation states that the force exerted by one object onto another, the gravitational force exerted by one object to another, is proportional to their object's masses and inversely proportional to the distance between them squared. This here is similar to the electric charge equation I have. Let me just write it out here larger and clearer. So let's say the mass of one object is big M and the mass of the other object is small m. Let's say r is the distance between them, r squared, and g is a gravitational constant, which I believe is 6.67 times 10 to the power minus 11 newtons meters squared kilograms to the minus 2. So this here describes to you the gravitational force exerted on an object. Next, we have gravitational field strength. So gravitational field strength at a certain point is the gravitational force per unit mass experienced by a small point mass m at any point in the field. So what this means to say is, if you have, let's say, a planet over here with a huge gravitational field around it, and let's say we have another object over here. So the gravitational force experienced by this object, let's say this has a mass of m and this has a mass of large m. You can use this over here to describe you the gravitational force. I'll just label that as r. This is the gravitational force. But when we're talking about gravitational field strength, what we're saying is that let's say we have a mass m, and let's say there's a theoretical point over here at the distance of r. So what gravitational field strength states that is what magnitude of force would that mass experience, and that's completely dependent by the mass. So the gravitational field strength, which is simply given by g, also what we know as gravitational acceleration due to gravity. Like I said, the force experienced per unit mass at any given distance. Now we can bring that down and over here, giving us g m m over r squared over m. M's cancel out, and we end up with g m over r squared. And this here is the same as the g you use in mechanics, the acceleration due to gravity, because if you think about it, acceleration due to gravity is the same as gravitational force divided by the mass that it's acting upon. And with that, we're done with gravitational field strength. There's one more thing I'd like to go along with you guys. Here's something that could potentially get asked: orbital motion. So they can ask you something like, let's say you have a planet over here and then a satellite. Let me try to draw something like a satellite, a really weird looking satellite, which is going around in circular motion. And let's say they ask you to determine the velocity of the satellite. They've given you that this planet has a mass. So let's say this planet has a mass m, and this planet has a mass of small m. The distance between them will be given by r. Now what would we do in such a case? So we equate gravitational force to be equal to the centripetal force, because this shuttle here has a constant velocity and the force towards the center of the circular motion. Let's draw out a circle to show the path that it takes. The center of the circular motion is the planet, which means the force acting towards the planet on this object is the same as the centripetal force. And you can equate that you can do gmm over r squared equals to mv squared over r, as we found out in the previous part. These two m's cancel out, that r cancels out, removing the square over here. We end up with v squared equals to gm over r, and v equals to root gm over r. That is the velocity of an object in circular motion. This is also covered in chapter 10 fields, but it can also get asked in the SL part, so I just decided to add it in. And also, let's say they ask you to find out the time period for its orbital motion. All you do is, in place of velocity, you put in our equation of 4 pi squared. Sorry, for velocity, not acceleration. For velocity, it's 2 pi times radius over time period squared, and equate this to root gm over r, as we found out from here. Actually, wait, hold on, I just stepped ahead a bit. We have velocity equals to that. Now if we square both sides, r squared over time period squared equals to gm over r. This r cancels out, getting rid of that square, and we end up with 1 over time period squared equals to gm over 4 pi squared r, and we have time period squared equals to, oops, the g is below, not above, 4 pi squared r over gm. And you can just root both sides if you want to find out the exact time period. But here's what you should do should they ask such a question. And that, I believe, is all that is there to circular motion and gravitation. Are there any questions before I shut off? Because that is all that is there to chapter 6. Nope, nothing more. Anyone else have anything to ask? Well then, okay, hold on, someone's typing. Will we be asked about non-constant gravitational field strengths? Nope, I doubt. I've never seen something come up. So it's fairly safe to assume that you won't be asked something like that. Alright then, I'll take it as no one else has any other questions and bring an end to today's session.